Thank you for standing by. Today's conference will begin momentarily. You will hear music until that time. Again, today's conference will begin momentarily. Thank you. Welcome, and thank you for standing by. At this time, all participants are in listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your phone to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to your host, Sarah Fraser. Thank you. You may begin.
Hi, everyone. Welcome, and thanks for joining today's media teleconference. I'm Sarah Fraser with NASA's Office of Communications. In the next couple weeks, a new CubeSat mission is going to launch to the moon. CAPSTONE will be the first spacecraft to fly in a near rectilinear halo orbit, the orbit intended for NASA's Gateway. CAPSTONE is short for Cislunar Autonomous Position System Technology Operations and Navigation Experiment. In addition to flying the near rectilinear halo orbit, CAPSTONE carries 2 technology demonstrations. So here today to talk more about the mission objectives, the spacecraft at launch, and the mission's connection to Gateway are Chris Baker, Small Spacecraft Technology Program Executive in NASA's Space Technology Mission Directorate, Brad Cheatham, Advanced Space CEO and Principal Investigator for CAPSTONE, Peter Beck, Rocket Lab Founder and CEO, Mark Bell, Terran Orbital Co-Founder, Chairman, and CEO, Nujun Moranci, Chief of the Exploration Mission Planning Office at NASA's Johnson Space Center in Houston. We'll start with opening comments from these speakers and then open it up to you for questions. To get into the question queue, as Danielle said, you will press star 1 on your phone. So to open it up, we will first hear from Chris Baker.
All right, thank you. Afternoon, everyone. We're looking forward to CAPSTONE's upcoming launch as early as June 6th from New Zealand. As you heard, CAPSTONE is the Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment, and it will be launching to deliver the first spacecraft to demonstrate the unique lunar orbit intended for NASA's Gateway. The 12U CubeSat will enter into the near rectilinear halo orbit to verify the dynamics and gain operational knowledge of this beneficial but challenging orbit. CAPSTONE is a rapid, low-cost, risk-tolerant demonstration that will also test multiple new capabilities with the intent to help lay a foundation for future small spacecraft missions and commercial support of missions beyond Earth. CAPSTONE is built around a firm fixed-price small business innovative research contract. The spacecraft is owned and operated by our commercial partners. The mission has its roots in small businesses and in the U.S. government's small business programs with multiple partners, including Advanced Space, Tyvak Nanosatellite Systems, part of Terran Orbital, Stellar Exploration, Tethers Unlimited, and Rocket Lab, all having been the recipients of current or prior Small Business Innovation Research Awards. So beyond our support of the Artemis program, part of what makes this mission compelling from my perspective is how it is pushing forward our desire to increase the pace of space exploration, the expansion of commercial space capabilities, helping support not just our major human exploration program, but also helping expand the capability of small missions to reach new destinations and operate in challenging new environments. So looking forward to answering your questions today.
Great, thank you, Chris. So next we'll go to Brad from Advanced Space.
Great, thank you, and thank you everyone for being on today. I'm very excited as we are getting approaching launch here for the CAPSTONE mission. I'm so happy to be here and share with you our perspective and answer your questions. I'd first also like to start by thanking Chris and his team at the Small Spacecraft Technology Program. This whole endeavor is critically dependent on the help they've provided, and so we appreciate that. And I also like to highlight that we're really proud at Advanced Space of the team that is supporting this mission, which is truly one mission team, including NASA, including our other industry partners and other government partners. And really just to highlight the breadth of that involvement, and Chris touched on this somewhat. Certainly the Small Spacecraft Technology Program is based in the Space Technology Mission Directorate, but the technology itself that it's enabling, a key enabling technology for this mission, I'll talk about in a minute, really initially started as a project in the Science Mission Directorate, and then on our path to getting CAPSTONE to where we are today was directly enabled and enhanced by support from the Exploration Mission Directorate. And so really it's been, I think, a broad NASA effort to get us to where we are today, and we're very grateful for that. And then also more specifically, we want to be really clear that the NASA centers have been really heavily involved. Our program office is at NASA Ames has been key day to day in how we've operated this. We have partners at NASA Goddard who are supporting some of our technology demonstrations, without which we can't demonstrate some of the key technologies, and their support has been critical and very helpful. Ongoing and active collaborations with the Johnson Space Center, and specifically the Gateway Program Office, which has provided inputs and received benefits from the work we've already been doing on CAPSTONE. Certainly NASA headquarters and also the Jet Propulsion Laboratory in many different ways has been key to getting us to where we are today. And so as we think as a small business that has been entrusted with this really important, critical pathfinding mission in CAPSTONE, we think it's really important to recognize that that's really a team effort, and all those folks at those different organizations have gotten us here, and we wouldn't have been here without them. Just to talk a little bit more about the mission, I'm grateful that the prior two speakers have spelled out the acronym because I have to do that all the time. But with the Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment, that's the CAPSTONE mission. The way I like to dive into those details a little more as we sort of think about it as two key activities. The first is the first four letters of the acronym, the Cislunar Autonomous Positioning System. And this is an advanced lunar navigation capability that here at Advanced Space has been in development for several years. We really see this as a foundation for future growth of operations at the moon, and supporting CAPSTONE has really gotten this system ready for flight. We'll be demonstrating it on the upcoming flight, and also has matured several different capabilities. Through that process, we've learned a lot that we think will improve this system going into the future to enable future missions of all types and kinds at the moon. The second four letters of the acronym, the Technology Operations and Navigation Experiment, this is sort of the second key for us, which is really we are focused here on demonstrating the ability to operate in these highly beneficial but also very unique orbits at the moon. As was mentioned, our target orbit is a near rectilinear halo orbit, which is part of a three-body Earth-Moon orbit family, and there's other missions that have done that before, but it's really a capability that has only been demonstrated in the previous mission, an Artemis mission, not to be confused by the Artemis program, by NASA, and has been flown by the Chinese space program. And so by flying CAPSTONE there in the coming weeks and months, we'll be only the third organization to demonstrate the ability to fly in these very unique and very beneficial orbits. And this is fundamentally an operational capability that we have demonstrated getting ready for launch, working with our partners at Terran Orbital, but it's also a capability that has yielded benefits that have already fed out to support other programs and other activities. So something we're very proud of getting to is having that system, the very unique system, ready to go. And so that's how we look at the mission as we approach launch. We're very excited. And I'll just sort of end here by saying I very much look forward to your questions. And we're extremely grateful here at Advanced Space to have great partners, many of them on this call, others not, that have delivered on this mission for NASA and for our nation. So thank you.
Thanks, Brad. I'm now going to pass it to Mark from Terran Orbital.
Great. Thank you, Sarah. And first I want to thank Chris Baker and the Small Spacecraft Technology Program and Brad from Advanced Space for entrusting us with the build of the satellite. We're proud of our 12U spacecraft we designed, offering fully redundant dual string bus, which is a new level of mission assurance in a small sat. We will be operating the satellite out of our Mach in Irvine, California, utilizing NASA's deep space network. And I just wanted to say, it was a great team to work with, and we thank everybody for all the support and all the confidence they had in us in delivering the satellite. And I'm going to turn it back to you, Sarah.
And Mark, this is Chris. I just also wanted to thank you for the support of the three spacecraft we currently have with you on the Transporter 5 launch, which is ongoing right now. So thanks to your team for the work on PTD3 and CPOD, and looking forward to seeing those deployed here shortly and getting in operation. So thank you, obviously, for CAPSTONE, but thank you for those as well, and looking forward to those operations as well soon.
Thank you, Chris, and we really appreciate the trust NASA has given in us into doing all these amazing programs, and look forward to many more in the future.
All right, thanks, Mark. Now we'll hear from Peter from Rocket Lab.
Yeah, thanks very much, Sarah, and echo all my colleagues here. A huge thanks to NASA and the whole team. I mean, it really was a whole team effort, and doing a mission like this is no easy task. But I guess what I'm most excited about is we're really, from Rocket Lab's perspective at least, bringing a new capability to go very far and do exciting things in deep space, at a budget and in a timeline that we've never really seen before. I mean, a small dedicated launch to the moon is pretty phenomenal, and there's been a lot of new capabilities that have been created to enable this mission, and the lunar photon is an incredibly high energy upper stage that we've spent a long time developing. So we're super excited to see it on the pad, and can't wait to get a safe launch and off to the moon.
Thanks, Peter. All right, I'll bring it back to NASA and pass it to Nujud to talk about CAPSTONE's connection to Gateway.
Thank you, and good afternoon. Yeah, this mission is an exciting milestone for so many aspects of NASA's Artemis mission. It goes without saying that we view the CAPSTONE mission as a whole as a valuable precursor, not just for Gateway, which we talk a lot about for CAPSTONE, but also for Orion and the Human Landing System in the larger architecture. CAPSTONE will gather important data on the Near Rectilinear Halo Orbit, or NRHO, and this is viewed as the orbit for Gateway and the vehicles it will interact with. So NRHO will undergird the success of not just Gateway, but many aspects of the Artemis mission, and that's for many reasons. NRHO enables global lunar access, in particular the South Pole, which is what we're interested in for the Artemis campaign. It's highly fuel efficient, especially when compared to other types of orbits around the moon. NRHO will give a gateway a continuous line of sight or view of Earth, so we get uninterrupted communication between the Earth and the moon. And as the gateway vehicle travels in deep space, its presence opens up a lot of opportunities for radiation experience and the greater analysis of space weather on people and instruments for future exploration. So the benefits of NRHO are clear, and we're excited to see CAPSTONE test and validate this orbit for the first time. Artemis teams like Gateway and Orion will use the data from CAPSTONE to validate our models, which will be important for operations and planning for the future missions. The NASA and Advanced Space teams have been collaborating very closely, for instance, working as one team on Gateway's mission design and trajectory, and there's been a lot of sharing back and forth of data and other activities. So it's been a very fruitful collaboration, and echoing the sentiments of everyone else on the call, we're excited to see CAPSTONE ready to fly, and that all of the Artemis teams are excited to watch it happen. Thank you.
Thanks. I think we're ready to start our Q&A now, so I will turn it over to Danielle to give those instructions and start opening up lines.
Thank you. As we begin the question and answer session, as a reminder, if you'd like to ask a question over the phone, please dial *1 and record your name when prompted. Your name is just required so we can introduce your question. Our first question today comes from Elizabeth Howell. Your line is now open.
Thanks for your time, everyone. This is probably for Bradley. Can you give me a sense about how you're going to be assessing success for this particular orbit, and also any kinds of lessons learned you might have imported from those two other missions, the Chinese one and the other Artemis?
Great. Yeah, thank you for that question. I'll start with the second part of that question, and I'll work back to the first one. So we have learned a lot from the Artemis mission, and a lot of that, honestly, has been personal transfer of knowledge. As I was really fortunate over a decade ago to be working at NASA's Goddard Space Flight Center supporting that mission, and that, in fact, inspired what I went on to do in grad school for my PhD. And so personally, that mission sort of started the passion that I had for these unique orbits that really led to the growth of advanced space and ultimately the CAPSTONE mission. So we certainly learned a lot about technically from that program about what some of the challenges are of operating in these orbits, and that fed a lot of research and work that happened in the intervening years that we'll now be demonstrating out for the CAPSTONE mission coming up here. And in terms of the first part of your question, in terms of quantifying success, we have several measurable objectives that we've identified from day one working with the NASA team. A lot of those get to validating the predicted fuel usage, validating the performance on both ground navigation, so predicted versus reality, as well as the operation or the demonstration of our cislunar autonomous positioning system. A key part of that is we have a great idea how that works in a lab here in Denver. We need to figure out how it works on a spacecraft at the moon, and there's a lot of nuance of those signals. Closing a cross-link between the CAPSTONE spacecraft and the Lunar Reconnaissance Orbiter, a system that certainly was not designed to do this experiment, but we've been working with the NASA Goddard team to be able to do this experiment. That activity already has yielded tremendous learning on what those future systems will need to be like so that we can have spacecraft at the moon talking to each other. And ultimately, during CAPSTONE, we'll learn a lot about that signal performance and the performance of the CAP system at the moon. Hopefully that addressed your questions, but happy to follow up if there is one.
Excellent. Thank you.
As a reminder, if you'd like to ask a question over the phone, please dial *1. And when you ask your question, please state your outlet. Our next question comes from Tim Fernholz. Your line is now open.
Hello, everyone. This is Tim Fernholz from Quartz. Thanks for taking my question. I think I understand the benefits of this new orbit to NASA's plans, but I'm not sure I understand the challenges. Could you talk a little bit about what makes an orbit like this challenging for a spacecraft to get to, and maybe compare it to either the Lunar Reconnaissance Orbiter's positioning or another spacecraft in orbit so we can sort of understand both the costs and the benefits? Thank you.
Brad, do you want to take that one?
Sure. Yeah. Thank you for that. That's a great question. And I think maybe I'll start. You mentioned at one point, getting to the orbit. And I think that's a key benefit of the near rectilinear halo orbit, is that it is accessible. And so I want to pull on that thread first, because the whole mission, CAPSTONE, from day one when it was first envisioned, is entirely enabled by this benefit of the NRHO, which is that we can use something called a ballistic lunar transfer to very efficiently get into this orbit, this NRHO. And to compare that, our approach to get there is on the order of tens of meters per second of fuel required, and if we were to do a direct transfer to a low lunar orbit, or to even a direct transfer to these type of 3-body orbits, we'd be talking about hundreds of meters per second of fuel. So it's basically an order of magnitude more efficient, and that is a key enabler for CAPSTONE, because from the beginning we were looking at a small spacecraft. And so in order to be able to do this mission, we had to know how to get there efficiently. And that's something that we've spent a lot of time developing those capabilities. And what those capabilities look like, to get to the root of your question, is really having the ability to design these transfers which change day to day and month to month. And there's a lot of availability, but they're not always the same. And so we had to develop the tools to be able to provide to Rocket Lab a launch target for them to be able to inject us on as a spacecraft, to be able to evaluate the environments and to evaluate the systems that are going to fly on the spacecraft itself during that transfer. And then when we get to the orbit, to get, I think, to the root of your question, a lot of what we're learning is about the operational realities of this type of flight. And what that means is we have to know how much ground tracking do we need to do to get an estimate of the spacecraft orbit that is sufficient to maintain the orbit doing station keeping maneuvers about once a week. And that really gets to some of these things of how do we get that done more efficiently, and are there ways where we can automate some of that navigation on the ground and some of that maneuver design activity on the ground so that the operational burden of the mission is reduced. Comparing an NRHO to something like the Lunar Reconnaissance Orbiter, one of the big differences from a math perspective, from a physics perspective, is the Lunar Reconnaissance Orbiter is flying much lower to the moon, and effectively is in an orbit about the moon. Is really, from a systems perspective, has to worry about the moon's gravity and being there. One of the challenges that we get for having such an accessible orbit in an NRHO is that the NRHO is influenced by both the Earth and the Moon. And for, we'll say the orbit's about 7 days, for about 6 days, it's really primarily influenced by the Earth. And then for a day or so, it's primarily influenced by the Moon. And so that combination of two bodies and the sort of evolution over a 7-day orbit of which is more dominant and which is more impactful, that really drives some of those operational complexities. Hopefully that got to the root of your question. If it didn't, happy to do a follow-up.
No, I think so. So basically it's the complexity of the various sort of arithmetic you have to do to figure out the precise course because the orbit is changing due to the 3 bodies affecting it. Is that fair to say?
Yeah, I think that's fair.
Thank you.
Yeah, and actually, so this is Chris Baker. I'm going to add a little bit more onto that. So, as Brad was saying, these are multi-body orbits. Another way to talk about the transfer is, one way it's referred to is a gravity manifold trajectory. You're using the pull of multiple different bodies, and then once you're in that near rectilinear halo orbit, you have the benefit of a lower energy entering into that from kind of an Earth frame of reference, and a lower energy leaving it to get to the lunar surface, and that's because you've got this pull from both the Earth and Moon, as Brad was just discussing. So it has the benefit of the low energy to get into and the low energy to get out of, but you are then now kind of riding this balance point between the gravitational pull of the Earth and the gravitational pull of the Moon, and that's, as was just said, that's what gets into that kind of complexity of making sure you know how to stay in that, how much energy it's going to take to stay in that balance point, and get that kind of operational experience before we go and do that with Gateway.
Our next question comes from Marcia.
Me? Can you hear me?
Hi, Marcia. Yes, we can hear you.
Yes. Oh, okay. Thank you. I'm just wondering, you mentioned 2 previous spacecraft in this orbit. When were those When were those launched, and do either of those missions help you in your planning for this one? And why is it taking so long to get to the moon? A couple-day trip in Apollo. So I'm just trying to. Is it because of this strange orbit you have to get into? Is that the reason for taking 3 months? I think I read online. Thanks.
So this is Chris Baker. I'll address the first part of that and then probably pass it back to Brad to discuss the more technical details of the orbital mechanics. But Brad, correct me if I'm wrong, but the comments you made earlier about the two previous spacecraft, that was in reference to operating in three-body orbits, not the near rectilinear halo orbit in particular. So this will be the first spacecraft to enter into and operate in that near rectilinear halo orbit. And the short version to the second half of your question is, yes, it is because we're using that low energy trajectory and we're using the pull from the sun to help us get to the moon that increases that timeline. It's a much more efficient transfer in terms of fuel usage, but it trades that efficiency for time. And then Brad, if you want to elaborate on the ins and outs of the orbital mechanics there, please do so.
Absolutely, yeah. Thank you, Chris. Great question. And so, yeah, as Chris was mentioning, the key there is really leveraging the sun's gravity in this case to more efficiently get to the moon, which enabled the whole thing. As part of your question was about the Artemis mission, and I might have misspoke. There's only two missions that have flown this. The Artemis mission flew two relatively small spacecraft in these Earth-Moon three-body orbits, as Chris clarified, not near rectilinear halo orbits, but a different type of three-body orbit. That was done in like the 2009 timeframe. I'll pull it for you. I'm sorry, I don't have it off the top of my head. And then the Chinese Space Agency is actually currently operating in a Earth-Moon L2 orbit with a relay capability for their far-side lander. So that's sort of the context. And then I think there was another part of your question, and I apologize. Could you refresh my memory of what the other part of your question was?
Well, I was just wondering why it takes so long to get there, and you sort of answered that. Yeah, and thank you for clarifying it. When I first heard you say, two previous spacecraft, I was thinking the same orbit. No, you answered that. Thank you. And if I might have another question on the cost, I saw two contracts listed online, launch about $10 million and CAPSTONE $13.7 million. Are those good numbers to use for the mission cost?
So this is Chris Baker. So the publicly available values are the total of the two contracts. The launch contract cost is still accurate. That's 19.95. The mission cost contract has grown a bit. It is now 19.98.
Thank you.
And just to clarify, I think I said 9.95 for the launch, but let me verify that I said that correctly. For launch cost, public value is $9.95 million, and the mission cost is $19.98 million. Apologies if I misspoke there.
Thank you very much.
Jude, I just wanted to clarify one piece too on the duration CAPSTONE is using to get there is the 3 months because of the ballistic lunar transfer, and that's to make it a low cost in terms of performance or fuel. When we travel to this orbit with the crew in Artemis, it would be as few as 5 days, potentially up to 10, which is really based around rendezvousing with the Gateway if it's the Orion vehicle. So very different travel times, whether we're traveling with crew or cargo type satellite. So more of 5-day type entry for crew in the future.
Yeah, thank you, Naju. This is Brad. I just also wanted to add on. You kind of mentioned in your question that the timing is vague in terms of how long that duration of that transfer is. Sorry, that's the second part of the question I was going to answer. And I just wanted to explain that. So one of the benefits of the transfer approach that we're using for CAPSTONE is that no matter which day we launch in the upcoming window, we will arrive at the same day. It's actually October 15th of this year. And so if you imagine if we launch, day one, it's one transfer, and if we launch during the window, it becomes a shorter transfer. And so that we've gotten some questions about that in the past, and it's really actually a feature of the approach because one of the key things of the specific operational NRHO we'll be flying is that this is a eclipse-free NRHO. So we'll it's designed to avoid eclipses from the Earth, which is a very important consideration. And so that's something that is sometimes missed. Duration changes depending on the day we launch, but in this window we will always arrive on October 15th. It's about 1:30 in the morning Mountain Time, and so all of our operational teams here and at Terran Orbital will be working the night shift to be ready to execute that activity. But I just wanted to get to the duration of why it's sort of the answer to the duration is it depends. So sorry for that ambiguity.
Our next question comes from Irene Quatz. Your line is now open.
Thanks very much. Good afternoon. I was just curious about the nominal mission duration and why there was that cost growth in the spacecraft cost. And then secondly, about just trying to understand too if this data is considered essential or just nice to have ahead of the Gateway and the Artemis program. Thanks.
Sure, thanks. So the mission nominally, up to 18 months, six month kind of baseline, and then up to 18 month operation. The short answer on the question of the cost growth is there were schedule impacts outside the scope of the original firm fixed price contract, and those schedule impacts resulted in that increased growth in the overall cost of the mission. And probably best person to answer the data question, maybe over to Najib.
Yes, thank you. So if anything goes wrong, we have full plans that we could move forward with Gateway and really all of the Artemis missions that will use NRHO. This data would be really valuable to help refine models, maybe find efficiencies, but it's not necessary or required to proceed. So always good to get more data and improve our modeling, but we have full confidence in the data that will be happening either way.
Thank you.
And this is Brad. If I can just add to that, thank you, Najib, for that. I think the other thing to highlight that I think is important is that, and Najib referred to this earlier, I'd say Capstone is already yielding benefits to the planning and the development efforts for Gateway and for Artemis. And so just to be super clear, our team is working day to day with the team at JSC to evaluate, different things that the Gateway team is learning that we can incorporate, and different things we're learning that they can incorporate already. And so I think that's just an important note that this has already, I think, yielded value, and operationally at least, as our teams have been collaborating through the development effort.
Our next question comes from Jeff Faust with Space News. Jeff, your line is now open.
Good afternoon. Question for Peter Beck. Just curious, if there are any special challenges or obstacles you had to overcome in the development of the lunar photon system to send CAPSTONE to the moon, and do you see any applicability of this technology for other missions, other applications beyond this particular mission? Thanks.
Yeah, great question, Jeff. Tremendous amount of new technologies developed, including an entirely new propulsion system called Hypercurie. Generally, small propulsion systems with really high ISP is a difficult thing to master. The propulsion system, Hypercurie, is a 320-second VAC ISP, full hypergol storable. So that was a tremendous amount of work. And then, on the vehicle itself, I think the largest lift we've done to date is around about 200 kgs, and this flight is in excess of 300 kgs. So lots of new developments, and probably one of the most exciting things is to your point, is that this is a really, really high performance, high delta V upper stage that we can use, for CAPSTONE, but it forms the basis of our mission to Venus and a bunch of other potential programs that have that really high delta V requirement and performance.
Thank you. Our next question comes from Ramin Gaba with Wired. Your line is now open.
Hi, thank you. I think this is a question for Brad Cheatham. I was wondering if you could say a little bit more about the two technology demonstrations. It sounded like there's a positioning system and a navigation system, especially if one of these are particularly new that you're testing out here.
Absolutely. Excuse me. Yes. Great question, and thanks for poking at that. The first key for us is the Cislunar Autonomous Positioning System, or CAPS, and that in and of itself is an architecture which will provide spacecraft operating in the Earth-Moon system or at the Moon with knowledge of where that spacecraft is. And so that is something certainly on the ground we take for granted. We have a GPS system to give us that information. Beyond Earth orbit into the Moon and beyond, that information is traditionally collected using ground-based tracking, where ground stations talk to satellite, and the ground figures out where the satellite is. So one of the key enablers for CAPS, as we see it, is providing that location information to a satellite on board the satellite. And so that will be the core of the technology demonstration for onboard activities. In that experiment, or in that technology mindset, we'll be evaluating data measurements that we'll be able to obtain by talking with the Lunar Reconnaissance Orbiter in low lunar orbit. From that communication with LRO, we'll get information on the distance and the time history of that distance between the two spacecraft. That will be used by the CAPS software to figure out where both spacecraft are. That's sort of the first key part of the demo. Another thing that we added to the program was also the inclusion of a second data type, which will utilize a chip scale atomic clock, or a CSAC, that will allow the spacecraft to listen to transmissions from the Earth, and just from receiving that information, be able to provide another type of information that would feed a positioning estimate for the spacecraft at the Moon. So the core piece on the satellite is based around CAPS, the Cislunar Autonomous Positioning System. The second key piece, and not necessarily in order of importance, but the second key piece I'll talk about is the ground technology, which I think you're alluding to, which is really to say the ability for a commercial company, in our case, to operate a satellite at the Moon in these unique orbits. That in of itself is a whole other technology activity that we've been able to develop and demonstrate as we've moved to launch. And so those are the two key pieces I think that you're asking about. And so CAPS is really the onboard knowledge of where the satellite is, and the ground-based flight dynamics system, which is really sort of the mission unique part of how to fly at the Moon. And then just to be really clear, and I'm happy to hand it off if you'd like to talk about it more, our partners at Terran Orbital will actually be the team sending the commands to the satellite and making sure that the rest of the satellite's working, besides just figuring out where it is and when it needs to do a maneuver. So I don't know if Mark had anything else you wanted to add there.
No, I think you pretty much covered it. Well, thank you. Unless you have a more detailed question, happy to answer it.
Yeah, actually, so this is Chris Baker. I'll add a little more on top of that too. So Mark, as he mentioned earlier, his team's got new technology on the spacecraft in terms of trying to increase the overall reliability. Pete just mentioned the new technology in the launch vehicle itself, and the interplanetary photon that is supporting not just this mission, but also potentially laying the groundwork for missions to Venus, missions to Mars. So in addition to the experiments on board the spacecraft, I'd say the overall mission is a risk-tolerant technology demonstration. This CAPSTONE at its core is a flight test, and it's a flight test of multiple capabilities. So we have these great onboard experiments, but the capabilities I think we're demonstrating are well beyond just those very powerful things that Brad was just talking about, extend to our spacecraft here, built by our partners, the launch vehicle, built by also by our other partners, and then kind of the overall mission capability that's being brought to bear here. So just the team at Advanced Space, Terran Orbital, Rocket Lab, Stellar Exploration, et cetera, have just done a fantastic job putting a lot of new technology and de-risking it for this mission. Really looking forward to how these systems all work. But just to emphasize, it is a flight test. It is a tech demo. So we will learn things. We've already learned things, and the technology that's been developed for this mission, we hope will go on to do great things in other missions as well.
Thank you. Our next question comes from Emily Speck with Fox Weather. Your line is now open.
Hi, my question is for Peter Beck. I believe I read that the lunar photon will continue on after separation for safe disposal. Where is that disposal orbit? And also, will data from this flight help with the future mission to Venus? Thank you.
Thanks, Emily. Yeah. So to answer the second part of your question first, absolutely. This is, and I think as Chris mentioned, this really lays the groundwork for future deep space missions, off Electron and other platforms. And the team has worked together to try and to really ensure that the end of life for the stage is in a safe and disposed orbit. And some of that depends on propellant residuals to what actual orbit we end up in. If we have a large amount of residuals, then we'll look to look for various different orbits that we can park.
Thank you. Our next question comes from Leonard David with Inside Outer Space. Your line is now open.
Okay, thank you. Can you hear me okay?
We can.
Okay, thanks. I guess for Brad, at some point I thought that the CAPSTONE would have a camera on it. I don't know if that's the case today. And just building on Jeff Faust's question for Peter, it looks to me like what we're seeing here is a kind of a stepping stone approach to deep space exploration with small payloads. And clearly Rocket Lab is very interested in follow-on missions. And to what degree do we kind of tip our cap to CAPSTONE for making this new milestone capable?
I think the first half of that was for Brad.
Yep, copy. Thank you, Leonard, for the question. I appreciate it. Good to hear from you. Yes, we do have a payload imager on board. We're very excited to have the satellite out there and to see what we can collect with that imager. It hasn't come up today just because that isn't in and of itself tied to a technology demonstration. That's more of a, why would you go to the moon without a camera, right? So we're looking forward to that, and we have ideas actually about how in that sort of enhanced mission phase, after we've gotten through some of the core technology demonstrations, to really understand how optical data could inform positioning at the moon, as well as exploring other uses for that data. So certainly that imager is in the satellite, is in New Zealand, and the spacecraft is fueled and ready to go, and that will be part of it. It's not right now at the core of any of the technology objectives. So thanks for the question.
And absolutely, Leonard. I think the tipping of the cap is a great way to put it. I mean, on the outset of the project, it looked relatively simple to do, but along the way, we had to create entirely new technologies. The hypercarry engine is electric pumped and it's an incredibly high mass fraction stage. So it forced us to do things that we wouldn't have normally done. And as a result, I think you're exactly right. It's created a capability, and we're excited to see that capability used right throughout our solar system for doing these really low cost and high value missions.
Thanks a lot.
Our next question comes from Deanne Divis with Navigation Outlook. Your line is now open.
Hi, thank you for the opportunity. I'm very curious about the navigation technology and what it might be saying for future plans. My understanding of what you're saying with the crosslink is the two satellites, CAPSTONE and LRO, will be swapping data, basically, with CAPSTONE getting data from LRO. But that suggests to me that the satellites know where they are relative to each other. If the goal is to not have to rely on the Earth, it seems like you would need some additional data points to say where a satellite is in 3D space. Am I getting that right? Is there a plan for in the longer term? I know it's just a test, but is there a plan to add additional data points from, say, satellites or the lunar surface to make all that work?
Yes, this is Brad. I'll answer that. Great question. Thank you. So just a couple of things to clarify. One minor thing is that in our crosslink with the Lunar Reconnaissance Orbiter, we're actually we're going to, as a spacecraft, the CAPSTONE spacecraft will imitate a ground station and will send a ranging tone to the Lunar Reconnaissance Orbiter. The LRO will turn around and send back to us. And so the baseline operation there, from just a mechanics perspective, is that they'll turn around the signal. From that, the CAPSTONE spacecraft, using the CAP software, will be able to estimate both spacecraft. And your question is very astute. Before we are able to do that, we have to know where each of them are, at least within the beam width of their antenna, right, in order to be able to talk to each other. So that is a great point. And so that is one of, as we envision the future of the system and the future of lunar operations, which you touched on at the end of your question, we have designed and architected CAPS from the beginning to be an expandable and an evolvable system. Fundamentally, we want it to be like a peer-to-peer network where multiple spacecraft are able to exchange information to figure out where they are, and that over time that system will grow and grow. The estimates will get better and better, but certainly there is an initial uncertainty or initial knowledge of the spacecraft that you have to begin that process, and really it's tied to the beam width of the antennas that you're using to talk to each other. And that's another reason why we've added for CAPSTONE this chip scale atomic clock. We call it the one-way uplink ranging, because you can envision, to get to that initial knowledge of where the satellites are, you can envision transmitting a broad beam from the ground to give you that initial estimate before you hand off to the spacecraft-to-spacecraft communications. So it's a great question. Thank you for asking it. You're very astute on the details there. And to really the bottom line is we see this as just the beginning of what we hope will be a much broader network among satellites and among assets, both could be on the surface, could be in different orbits at the moon, but really that's what the system has been architected to do. So thank you for the question.
So you could add assets on the surface to, like some of the other systems I'm familiar with, to get it down to a very accurate 3D location?
Absolutely, yeah. And part of the enabling science, if you will, for CAPS is that because the Earth-Moon dynamics for these type of three-body orbits is not symmetrical like an orbit just about the Earth or just about the Moon would be, those relative measurements in a theoretical orbit determination approach can actually yield absolute knowledge of where they are in space, because we don't have a symmetry with which to complicate the orbit determination approach. So, and the other part of the question, absolutely, ground nodes will help in the future. One of the key guiding philosophies as we've been developing this for several years has been to really try to focus on the minimum viable product, realizing that the systems that probably are in most need of additional navigation support are probably the smaller missions to begin with, right? And so that's something where we see this as an enabler to more missions like CAPSTONE. And as there are assets on the surface, they will certainly, we would like them to be part of the network and make them part of the solution. Absolutely.
Thank you. Very interesting.
As a reminder, if you'd like to ask a question over the phone, please dial *1 and record your name when prompted. Our next question comes from Jim McKenna with Aerospace Tech Review. Your line is now open.
Thank you. Can you hear me?
Yes, we can.
Great, thanks. This is for Brad. You mentioned the ability to avoid an Earth eclipse. Is the plan for this spacecraft to be in an orbit that has it always facing the Earth, and rather than going behind the Moon? And is that a capability that's attributable to this distinct orbit?
Absolutely, yes, Jim. Thank you. I'll answer that, and then I'll also hand it over to Najud to see if there's anything general she'd like to add. But yes, to answer your question, what we'll be designing is a specific phase of the NRHO so that we are not in an eclipse from the Earth. Another key benefit, which I don't think we've talked about, or if we have, I'll reiterate it, is that this orbit, this unique orbit, is always in view of the Earth. So we are never behind the moon as you look from the Earth, and the phasing of the orbit itself, the first part of the response, is that we're also timed so that we're never flying through the shadow of the Earth. As you can imagine, that moves around the lunar distance. And so those are the two key things. And the reason why I mentioned Najud is because this is the exact same approach that Gateway is taking. In fact, we are designing all of our CAPSTONE mission operations around the orbit that is planned for Gateway. So this gets to part of that operational experience. And part of that gets to, as I mentioned earlier, the launch timing and the approach to get to the orbit are very sensitive to that phasing, and so that's an approach that the ballistic transfer helps us address. But I also want to hand it back over to Najud, and if there's anything else from a Gateway perspective that she wants to add.
Yeah, thank you, Brad. Also I'll note the specific resonance Brad is talking about is a 9-2 synodic resonance, which means for every 2 months, we'll pass through 9 orbits. So it's a very specific NRHO. There's actually a whole family of NRHOs, but we've chosen a very specific one for the Gateway and Artemis missions, which really avoids those Earth eclipses, which can be multiple hours in length. So to design vehicles to survive multiple hours of eclipsing would be far too challenging. This doesn't mean that they will never see eclipsing, because we will pass behind the moon when we're very close to the moon every once in a while, but those eclipses are less than 90 minutes. They're generally in the 70 or 80-minute range, but those are lunar eclipses, not Earth eclipsing. So as Brad discussed, right, this orbit was very carefully tailored to support the longer missions, because we don't want to build vehicles out for those long Earth eclipsing, which would add a lot of performance, really battery mass and power systems that you'd need, as well as thermal systems. So if there's any follow-up, but yeah, this is very important on the timing for this orbit.
Great.
We have no further questions in queue. So Sarah, back to you.
All right, thank you, everyone. Really appreciate you joining the telecon. In about an hour, you'll be able to listen to a replay of this teleconference by dialing 203-369-3272, and that replay will be available for 30 days. There's also a YouTube stream currently embedded on nasa.gov/live. So if you go to that page and check out the YouTube link, you can listen to it there as well, and that'll be available forever. And if you need that information or have any follow-up questions or interview requests, you can reach out to Jarrell Dodson, who you RSVP'd to, or to me, Sarah Frazier, at sarah.frazier@nasa.gov. That's sarah.frazier@nasa.gov. And we hope that you'll tune in for the launch, targeted for no earlier than June 6th. So the launch will be covered live on NASA TV. So please keep an eye out on nasa.gov/live for details on how to watch. We'll add that information as we get closer to the launch date. And thank you all very much.
That concludes today's conference. Thank you all for participating. You may disconnect at this time.